So in this video, we're going to be continuing in section 2.6 on related rates. So we've already talked about implicit differentiation at this point, and we will be using that skill again to help us solve related rates problems. So in example 1, we have that a pebble thrown into a pond causes circular ripples to radiate outward. If the radius of the outer ripple is growing by 2 feet per second, how fast is the area of the circle growing at the moment when the radius is 10 feet? So let's start by just visualizing this. A pebble is thrown into a pond and it begins to create ripples. And those ripples grow larger and larger and larger. They're circular ripples. We have a few pieces of information here, and we also have what we are looking for. So let's start with what we are looking for. How fast is the area of the circle growing? So we want to know how fast is the area changing. So ultimately, what we want in this problem is we want dA dt. So not just area, but how fast is it changing? What is the rate of change of the area? We want the derivative of the area, and more specifically, we want it when the radius is 10 feet. So we want dA dt when r is equal to 10 feet. Okay. So let's think about our variables that we have in this problem. And we're also going to think about whether they're changing or whether they're not changing. So we do have the area of this problem. We do have area of these circles, and the area is changing. If it's changing, that means it has a rate of change. If it has a rate of change, that means it has a derivative, a dA dt, which we can already see. We've already said we want to find dA dt. Another variable that we have is the radius r, which is also changing. As these circles continue to expand, their radii are getting bigger. So if r is changing, that means it has a rate of change. That would be dr dt. So we want to find dA dt. Let's just start with a simple formula for the area of a circle. We're talking about circles here. The area of a circle is pi r squared. I'm going to differentiate both sides of this equation the same way we did when we did implicit differentiation. It's just that this time we're taking the derivative with respect to time because these things are changing with respect to time. So I want d dt of the area and d dt of pi r squared. We're taking the derivative of both sides of this equation. On the left side, the derivative of the area with respect to time is simply dA dt. On the right side, the pi is a constant, so we can use the constant multiple rule and just pull that out. And now we need to take the derivative of this r squared. We bring the exponent of 2 down. The new exponent on r is 1, but r is changing, and so it does have a derivative, dr dt. Now I'm just going to clean this equation up. So we have dA dt is equal to 2 pi r dr dt. We wanted dA dt when r is equal to 10. So I'm going to plug in 10 for r. And then for dr dt, well, they told us in the problem that the radius of the outer ripple is growing by 2 feet per second. The radius is growing by 2 feet per second. So that 2 feet per second is dr dt. It tells us the rate of change of the radius. So dr dt is equal to 2. So now we're able to finish calculating this. We have 2 times 10 times 2, which is 40. And there's a pi there. So our dA dt is equal to 40 pi, and this would be measured in feet squared per second because area is measured in feet squared and time is measured in seconds. So generally speaking, how do we solve a related rates problem? We determine which quantities are changing with time. So that's when we went over here and talked about what are our variables and which ones of them are changing with respect to time. In this case, both of our variables were changing with respect to time. We then went on to find an equation that relates these variables. Sometimes it's useful to help make a diagram. So we did make a diagram, and we also started with an equation that relates those variables, simply the area of a circle. We then went in and we differentiated both sides of the equation implicitly with respect to t. So that's when we came in and we put these ddt's on both sides of that equation. After we had that derivative, very important here, after we took the derivative, then we substitute into the new equation any values that we have. So we took the derivative, and once we had the derivative, then we were able to come in and substitute in r is equal to 10 and dr dt is equal to 2. So one thing to keep in mind as you work on related rates problems is do not plug any values in until after you have taken the derivative. And then we were able to finish number 5, solving for any remaining derivatives and interpret our answer as a rate of change. So we did make sure to include units here. So what this answer is telling us is that the area of these circles is changing at a rate of 40 pi feet squared per second when the radius is 10. So whichever one of these circles has a radius of 10, at that moment, the area is changing at that rate. Example 3, we have a boatyard's total profit from selling X outboard motors is given by this function here. If the outboards are selling at a rate of 20 per week, how fast is the profit changing when 400 motors have been sold? So let's start with what we want. How fast is the profit changing when 400 motors have been sold? Is dp dt when X is equal to 400. X represents the number of motors, X is outboard motors there. And we do want dp dt because their profit function is changing with respect to time. Profit is changing with respect to time. All of our related rates problems are going to be changing as time goes on. They tell us that they're selling at a rate of 20 per week. So their profit is changing depending on time. So let's go in and differentiate both sides of the equation. So I don't really need to make a diagram for this. One thing I will go back, let's talk about which variables are, number one, let's talk about which variables are changing with respect to time. So in this case, the variables we have are P, the profit, and that is changing with respect to t. The other variable we have is X. That's the number of outboard motors that they're selling. That is also changing. More specifically, we know exactly how fast that is changing. They tell us that the outboards are selling at a rate of 20 per week. So the rate that they're selling at is equal to 20 per week. So we know dx dt is 20. They want us to find how fast is the profit changing when X is equal to 400. Okay, so we're going to come into the equation that we were given. So we don't really have to do step 2 in this problem because we were explicitly given the formula for the profit. So it's not like the first one where we had to write the area of a circle. Now let's come in and differentiate both sides of this equation implicitly with respect to t. So we're taking d dt of every term that is in this equation. So I'm just going to set up my d dt's, and then we'll come in and put each term of the equation on the inside of this. So on the left side, there's a p. Right side, there's a negative x squared, there's 1000x, and then there's a 2,000. I already put that minus sign right there for the negative 2,000. So now let's start differentiating. The derivative of p with respect to t is dp dt. The derivative of negative x squared with respect to t. So we have to be careful here. I know we're used to thinking of x as our independent variable, but it is not. T is our independent variable. T is what we're taking the derivative of with respect to. So we bring the exponent of 2 down. The new exponent on x is 1. But remember, x is changing, so x has a derivative. We talked about that when we discussed our variables. So we do need to put a dx dt after that. Plus the derivative of 1,000x. Well, the 1,000 is just a constant, so that will just stay there. And the derivative of x is dx dt. And then finally, the derivative of that 2,000 is simply 0. So now we have an expression for dp dt. More specifically, we want dp dt when x is equal to 400. So I'm going to plug 400 into the equation that we have for the derivative for x. So that's negative 2 times 400. dx dt we know is 20. dx dt is the rate of change at which they're selling at each week. We know that's 20 plus 1,000 times dx dt again, that is 20. So this gives us a negative 16,000 plus 20,000, which comes out to be 4,000. So what does this tell us? So interpreting this, we found the rate of change of the profit. So that tells us that the company's profit is growing at the rate of $4,000. With respect to time, time is measured in weeks in this problem, so $4,000 per week when, this was when x was equal to 400, so when they are selling 400 outboard motors. So in example 4, we have that a study of an urban population predicts that sulfur oxide emissions in a city will be S is equal to this quadratic function, tons. So we're measuring pollution in tons, and it's depending on x. They go on to then tell us that x is the population in thousands. The population of the city T years from now is expected to be that many people in thousands. We're asked to find how rapidly the sulfur oxide population will be increasing 4 years from now. So ultimately, what we want is ds dt when t is equal to 4. Ooh, that looks crazy. When t is equal to 4. So let's take a second to think about our variables and to think about what is changing in here. So S is the amount of population. That's definitely changing. We expect population to go up, or rather pollution. S is the amount of our pollution. Pollution we expect to increase as the population increases, so S is changing, which means that it does have a derivative. We know it does. That's what we're looking for, in fact. Another variable we have is X, which is the population. The population is also changing. So if the population is changing, that means that we do expect for there to be a dx dt. Okay, so we want ds dt. So I'm going to start with the equation for S. And I'm going to differentiate both sides of it with respect to t. So we're coming in and taking the derivative of both sides of this equation, all 4 terms, with respect to t. So I'm just applying a derivative operator in front of all of these terms. And now let's come in and start differentiating. The derivative of s with respect to t is ds dt. The derivative of 2 with respect to t is 0. The derivative of 20x with respect to t, so the 20 is a constant, and the derivative of x is not 1, because x is changing. So it is dx dt. In related rates problems, t is what we usually think of as x. So, usually we think, oh, the derivative of x is 1, not in related rates problems, because x represents some other variable, in this case, the population. So it does have a derivative and it is changing. Moving on to our last term, the 0.1 is a constant, so I'll keep that down in front. We'll bring the exponent on the x down. So we have a 2 in front. The new exponent on x is 1. And then we will multiply by the derivative of x, which is dx dt. So there's that chain rule coming in there. So I'm just going to clean up this equation here by multiplying that 0.1 and that 2 to get a 0.2x dx dt. Now, what we want is ds dt when t is equal to 4. But we don't see where we can plug t into this equation. What we do have is we have some x's, and then we have some dx dt's. Okay, so I'm going to go to the x equation, which tells us that x is equal to 800 plus 20 times the square root of t. We're going to take the derivative of this equation so that we can have dx dt. So the derivative of 800 is simply 0. The 20 is a constant in front. The exponent on that t is a 1/2 that needs to come down. And then the new exponent on that t will be a negative 1/2. We do not need to use chain rule now because the derivative of t is just 1. Right, so I don't have to write that. We're taking the derivative with respect to t. So just cleaning this up here, we have 20 divided by 2, or 20 times 1/2, which is 10. And then I will stick that t to the negative 1/2 in the denominator as a square root. So now we have an expression for dx dt, and I'm actually going to come back into... We have two options here. We could come back in and substitute in this dx dt into these two places right there. But we do know that we're looking for this specifically when t is equal to 4. So I can also just go ahead and say, well, when t is equal to 4, dx dt would be 10 divided by the square root of 4. So that's 10 divided by 2, which is 5. So I now know what I want to plug in for my dx dt's. So this is 20 times 5 plus 0.2x. Well, x is this here. This 800 plus 20 root t. And then there's a dx dt on the end of that, so there's a 5 there. And remember, we were looking for ds dt when t was equal to 4. So I'm going to go into this equation and plug in a 4 for that t right there. And then we will evaluate this. At this point, I can really just plug all this into the calculator just to make sure we're clear on where everything's coming from. This 5 was this dx dt. All of this right here is x. We plugged in what we were given for x in the problem up here. And then again, this 5 is the dx dt that we see right there again. If we punch all this into the calculator, we will get 940. So now let us interpret that. So what that means is, let me make this a little bit larger. So we have, therefore, in 4 years, that's the t value that we plugged in. And what are we talking about? Well, we're talking about the sulfur oxide emissions. The sulfur oxide emissions will be increasing or decreasing. Depends on if the derivative is positive or negative. 940 is a positive number, so they will be increasing at the rate of 940. Let's think about what unit we want to use. This is ds dt. S is measured in tons, and T is measured in years. So that is 940 tons per year.